Thanks, first of all, to the organizers for the chance to speak at this very fun conference in a beautiful place. Yeah. We scheduled our talks, knowing that I could piggyback on the setup from Akshay. So I'll get straight into the stuff I've been thinking about very recently. This is a work in progress with some people at Brown. Right. So there was the paper last year that showed that generic EFT generation gravity failed Jacobi. There's a constrained subset of EFT coefficients where it's still satisfied, and then they had the follow. Rather than working with celestial soft currents, they just worked with a residue condition on hard momentum space amplitudes and found the exact same constrained subset of EFT coefficients. So whether or not those conditions are exactly the same, it seems that the constraints they got, like they're probing the exact same concepts there. Right. So we're all familiar how in 2D CFT you can compute the commutator of currents using contour integrals and residues. And when you have currents, you can write the Jacobi identity in terms of this double residue condition, is what I'm going to be referring to it as. I suppose I should put a question mark over the equal sign there. Right. So we're all familiar with this simple argument from CFT. So how can it fail for amplitudes, which also have the same collinear poles that look like a CFT? They've got the global conformal invariance, but well, the answer is simple, that hard amplitudes have non-local poles also, and that the CFT argument, it relies on locality, and when you pull the contours around, they need to not be passing through other poles. Right, and I should say that this is just a work in progress. We haven't proven that this is the only obstruction, but it seems to be working out very well. Right. So specifically, if we have three positive helicity particles, gluons or gravitons, we should have in mind, and then we're wondering whether they give an algebra that satisfies Jacobi. Then this three-particle channel propagator it seems to be the key obstruction for both the soft and hard cases. The obstruction seems to come down just to this propagator. But the first half of the talk is going to be more detail on the hard case, and then I'll get into the soft. Right. So if we expand this out in terms of our omega, z, and z bar kinematic variables, then we've got a denominator that's linear in Z1. So it's going to have a simple pole in Z1 somewhere, and it's not going to be at Z2 nor Z3. And such a function fails this double residue condition. So qualitatively, we can just use a simple function like this. And then this first residue here is 2 to 3. There's no pole, so that's 0. This first residue here is 1 to 3. There's no pole, so that's 0. And then this term is 1 to 2, which does have a pole. And then once you set 1 to 2, then the whole denominator is Z2, 3. And then you take the Z2, 3 pole, and then you get a non-zero residue. So overall, this fails the double residue condition. Right. If we take this 1 to 2 residue, yeah, that leaves you with 1 over Z2, 3.
I guess it's not self-evident to me that that this is the same as just taking sequential poles of operators and circles around one another.
Oh, my back button is not working. Maybe. Ah, geez. Okay, the computer is also not controlling the slides. Oh, maybe it's just really slow. But were you asking about this
Yeah,
being equivalent? Yeah.
But in conformal field theory, wouldn't we expect Z12, Z23, Z31
Yes.
for a bunch of dimension one operators?
Or you're asking, do we expect poles at those locations?
Yeah.
Yes. And not at other locations.
No, just that the 3-point correlator would be like Z12, Z23.
Oh,
Z3.
Right. Yeah, the 3-point would have some powers to that, but for the OPE for OPE we usually have in mind like arbitrary other insertions further away. But sure, yeah, we could take that special case.
But then if you have the form that's dictated by conformal invariance, you would never get a violation in those associativity, right?
Mm-hmm.
So this expression isn't conformally invariant that you're writing down?
Well, it must be conformally invariant just because the amplitudes are Lorentz invariant or covariant. So as long as you have more insertions, then it's probably possible to have non-local poles be consistent with global conformal invariance. But maybe if you only have 3 insertions, then global conformal invariance only allows local poles or delta functions.
Okay. Are you saying that this is something that happens here that doesn't happen in conventional conformal field theories?
Yes, we almost always work with local CFTs that have only local singularities.
But these look like local singularities to me. There's a singularity when Z1 goes to Z2, one when Z2 goes to Z3. Why aren't those local singularities?
Right. So those residues are probing local singularities, but to get that relation between the residues, the argument involves pulling a contour, taking a tiny contour, blowing it up to a finite one, wrapping it around some other things, and this argument relies on not passing through other poles.
Okay, but so that expression you got before could have come up. So you're not exactly taking the operators towards one another.
This within the amplitude context, when we calculate this residue, we are taking the insertions towards each other. But for the soft case, the operators are not necessarily local then, and for the hard case, you've got other poles.
Where is the step where you're doing something that you wouldn't ordinarily do in conformal field theory? Because surely that previous expression would have come up in ordinary conformal field theory.
Yeah, that in ordinary conformal field theory, you wouldn't have like a pole in Z1 that's at some random point. You would only have the poles at like Z2 and Z3.
Oh, you mean because you're adding 2 terms?
Right, because the denominator is not overall proportional to Z1, 2.
I see. No, I think you do get that if you go like, what if you do a correlation between e to the I p1 dot x and e to the I p2 dot x? Isn't this exactly what you get?
And so, well, I mean,
This is
as long as you're normal ordering.
This is exactly the 2-point function that you would get if you took e to the p1 dot x plus p2 dot x, e to the I p2 dot x, e to the I p3 dot x.
No, I mean, as long as you take the normal ordered vertex operators, then they still obey the usual 2-point function, where it's just a power of z1 2.
It would be 1 over p1 plus p2. Oh, it would be z minus. Yeah.
Right. Yeah. Yeah. It's also got that problem or difference.
How do I see that that doesn't arise in the CFT?
Let's see. As well, this also has a pole in Z1 that's not at 2 or 3, nor at some other insertion.
How do I prove in a CFT that I only get poles at the sort of obvious locations?
It's like one of the axioms for a local CFT or within the Euclidean context. I've usually heard locality defined as you only have singularities when you go to some other insertion.
Or rational CFT.
Okay, well, yeah. So whether or not there exist CFTs with the non-local singularities, it's still seems to be the culprit for this Jacobi failure. Right. So it's coming from this 3-particle propagator, which contributes to the amplitude through its factorization channel. So if you've got some amplitude with 3 positive helicity insertions and arbitrary others, then it has factorization channels where you have those 3 positive helicity particles and 1 other particle, and times that other particle with whatever the rest of the insertions were. Where I'm summing over the other particles in the theory X. And yeah, if all such 4-point amplitudes vanish exactly, then it seems that there's no obstruction to associativity. So for example, in integrable theories where the 4 and higher point amplitudes vanish, then those theories will have no non-local poles. And then right away that it seems a lot more hopeful that you can match them onto simple familiar CFTs, which goes part of the way to explain why twistor theory has seen a lot of recent success in getting OPEs that are similar to known CFTs. Right. Because twistor theory can describe several integrable theories on spacetime.
So all of the examples of this non-locality can only be seen once you've got 3-particle momenta. When you've got at least 3 particles on each side of your factorization channel. Because I thought the sort of Costello-Paquette examples only had 2 particles on one side of the.
Well, Costello-Paquette mostly worked with form factors, right? Yeah, that's probably different enough to explain that. But yeah. You probably need 6, and for most theories 7 or higher point to really see these if you want to work with explicit amplitudes.
What if you're going to like 3-to-1 scattering? Don't you always encounter that?
Right. The 4-point amplitude diagnosing the obstruction to associativity, it doesn't mean that the 4-point amplitude will itself give a singularity that causes problems for it. It's just that this propagator is the core obstruction, and the 4-point amplitude tells you about the residue of that propagator. So when you have a high enough point amplitude to see that contribution, then you should be able to see explicitly the Jacobi failure.
So you're saying that if we do a conformal block expansion of a conformal field theory, we shouldn't, the formula, the 4-point amplitude is CIJK, sum over kth conformal block, CIJK squared sum over k. That formula in general is wrong because it's a rigidity violation.
It's difficult to guess how things should work for lower point. Once the delta function becomes important. As well, I'm talking about arbitrarily high point.
No, but for 4-point, it's already relevant. And that's where people do the conformal block expansion.
Right.
It seems that things that appear there, you're calling a non-local singularity.
As well, when you get below like 6 points, then this other amplitude with x ... is going to start being very low point, and then this might end up vanishing because of this ax ... rather than because of the 4.1.
Oh, I thought you were saying that at 4-point you just had a pure 4-point that didn't involve a sum over conformal block. No, you weren't saying that.
No.
But how do you know how to compute the 3-point if it's not associated? Yeah, let me put that another way. In general, the 4-dimensional conformal field theories in momentum space would seem to fall under this category. And I think you're saying that in general, their OP is not associative when you've got 3 things going on. And and you need that OP to compute 4-point.
Yeah. Celestial amplitudes, it's still not well understood.
It has nothing to do with going into conformal primary basis. Your funny singularities occurred before you transformed omega.
Yeah, but just it's difficult to understand the low point amplitudes from the CFT perspective, right?
Well, it's more difficult if you try to also talk at the same time about transforming to a Mellon basis. If there's some trouble with associativity, before you do that transform, it would be good to understand that in the language of ordinary quantum field theory. Or do you think there's no trouble there for some reason?
Yeah.
I don't think there would be a quantum field theorist who thought that the operator product expansion was not associated.
Right. So there are like two senses of associativity, at least. there's the one that's often used in Bootstrap where you to take two insertions and you use the full OPE, the full series that converges, and you can trade for conformal blocks, and then you do subsequently with another one, and then you can do that to compute correlators, and doing that in different orders should give the same answer. So yeah, and then a separate sense of using modes of operators to compute commutators, which defines some algebra, and then talking about whether that bracket is associative. Yeah, and they're related surely, but yeah, but they're distinct concepts, and the statements about the low point amplitudes I think are more related to that bootstrap sense of associativity rather than the like bracket sense of it.
But presumably there's a way of thinking about it in the former case.
Mm-hmm.
That doesn't seem to have been
right. But the collinear limit just tells us about like the singular part of the OPE, and like we're not close to having a convergent expression for it with positive powers of Z1, 2.
Oh, I thought the collinear expansion had been developed in excruciating detail by accelerator people. There's conferences with thousands of people going to them on it.
Yeah.
Yeah.
Thanks. Right. So, yeah. You could set the 4-point amplitudes of plus anything to 0 to get rid of the non-local singularities, but that's stricter than necessary to just make to just save Jacobi. For saving Jacobi, you can still allow some non-local poles as long as they vanish in the collinear limit. And for these 4-point amplitudes, once you take a double collinear limit, then Z1, 2, and 3, they're all the same value pretty much. And then by momentum conservation, Z4 is also going to have to take that same value. So Zij for any of 1, 2, 3, 4, it's going to be small. So as long as you have an expression for these 4-point amplitudes, you can just read off based on counting the powers of all the angle brackets. And if that power is overall positive, then it's going to vanish on its own, and then you don't have to worry about setting that amplitude to 0. But if it's a 0 or negative overall power, then it is an obstruction to associativity. And if you want to demand associativity, then you need to tune your EFT coefficients to make that amplitude 0. So for example, from Einstein plus a scalar plus an R cubed term, if you take the 4 positive Felicity graviton amplitude, then you get this expression, and we've got 1 angle bracket in the numerator and 2 in the denominator. So when you take the double collinear limit, it's going to stay finite. It's going to blow up actually. So if you want associativity, then you need to tune your coefficients to make that 0. But the plus minus, which conspicuously from the previous talk was allowed to be non-zero, you can look at the angle brackets and see that it's there's more in the numerator than the denominator. So this will vanish automatically in the double collinear limit, and there's no reason to constrain your coefficients for it. And then the plus scalar amplitude, this also stays finite in the double collinear limit, which we can read off by counting the powers of the angle brackets. And then they also found that this was necessary to set to 0. Okay, so I'm finished with the hard part of the talk, and I'll go on to the soft part now. Right. So oh yeah, and I'll work in momentum space, but it doesn't actually really matter because the momentum space soft limit and the conformally soft limit, they grab the same objects. Yeah, like this your insertion in momentum space depends on omega, z, and z bar, but once we just grab this soft expansion coefficient, then it only depends on z and z bar. So it's a moot point of whether you're momentum or melon. But right, and then rather than just defining this OK, I'm going to define an operator sk that grabs the coefficient of omega to the negative k. It's going to be useful to have that notation so I can be clear about the order of limits when I'm taking multiple things soft. And it's very important that soft insertions have only local poles. You can just think diagrammatically and see that when you Taylor expand the propagators with more than 2 momenta, then it just gives polynomials in terms within the series, and you no longer have the non-local poles from those terms. Right. So if soft insertions have only local poles, then what's the obstruction to Jacobi? Well, it's that the order of soft limits matters. And this also comes from this 3-particle propagator. If you just Taylor expand it in omega 1 and then omega 2 versus omega 2 and then omega 1, you get different series. And I wrote down the expression before. It's a little messy looking to take in, digest in a few seconds. So it's qualitatively the same as just 1 over omega 1 plus omega 2 for this purpose. So if we expand that, then it's a geometric series basically. And this only has positive powers of omega 1, whereas this only has negative powers of omega 1. So you get very different expansions when you take the different orders. And this means that if I grab a certain power of omega 1 and then a certain power of omega 2, the order in which I do that is going to matter. But the limits used within the literature so far to compute these the current algebras, it was implicitly using a limit like this, where you start with a hard thing, and then you take a residue, and then you take a soft limit, and then you take another residue, and then another soft limit. But doing this for like residue 1, 3, 2, 3 versus 2, 3, 1, 3, you'll notice that you end up using the soft limits in the opposite order. And those don't commute, so you're not actually taking residues of the same object. So you then shouldn't expect that double residue condition to be satisfied, because that was a condition for a single object that has only local poles, whereas here you end up using 2 different objects. Right. So we can, and it seems most natural to me to take the soft limits first, choose some order. Say to one soft first.
First one, wouldn't that be natural to interpret that object as the commutator of S1 and S2?
Where, sorry?
On the previous slide, would that be how we would just in CFT compute the commutator of S1 with S2? First, we would take a contour integral around one, and then the contour.
Right. So the commutator for between two soft currents is still decently behaved, but here this is like the action of a soft current on O3 followed by the action of a different soft current on O3, where O3 is just some hard insertion.
But in just a 2D well-behaved, current algebra, we wouldn't talk about things like that. We would talk about commutators, right?
That's well. Oh no, in CFT you've got the state operator correspondence, and you can act on states with charges, and you compute that with a contour integral. But yes, we also could we also could take all three soft and then just talk about commutators of currents. But I left one hard, so there's only 2 orders to choose rather than 6 orders to choose for the soft limits. Right. But we also could define this single object where we take the soft limits first, and then the order matters. Let's just choose to take S1 soft or particle 1 soft first, and then it gives you an object that has only local poles in Z1, 2, and 3. And the contour pulling argument does apply now, and this has to satisfy the double residue condition. And you can also check this explicitly. I've checked it confidently for the sub-leading Yang-Mills, and less confidently for all of Yang-Mills, or plus F cubed. Right. So all is well then, maybe. We've got an object that satisfies the double residue condition, which we recognize as Jacobi for current algebras. But it's still a little strange, because for example, right, if we're trying to calculate the action of soft current 2 on hard insertion 3, so just something that should be local happening between 2 and 3, then you get a different result depending on whether particle 1 is taken soft before or after computing that action. So in that sense, it seems like once you start having multiple soft currents, then they're no longer local operators, or they no longer look like local CFT operators. Like it matters what's happening far away. Right. Yeah. So for the hard case, the obstruction seems to be non-local poles, whereas for the soft case, the obstruction seems to be that multiple soft currents are non-local operators. Yeah, which is an interesting contrast with a single soft insertion, which is just beautifully recognizable as CFT properties. But yeah, the soft theorem's not commuting was a point of confusion for a while, but the understanding has advanced recently, and it's related to curvature on field space, which is a beautiful, rich structure. So that makes me hopeful that this strange behavior described here with the order of soft limits mattering and seeming non-local for the CFT side. I'm hopeful that can also be understood in terms of some rich curvature on field space type structure, and that's putting a lot of pressure on Dan. But I'm looking forward to his talk. So, okay, I'm done.
So you obtain this non-associativity by looking at the propagator involving 3 particles. Is it obvious that if you consider even larger number of particles that you don't get additional constraints that arise?
Well, it'll catch up eventually, but right. Yeah. Think about the example I gave of 1 over omega 1 plus omega 2, and if you do the Taylor expansions in different orders, you get different things. If you had instead 1 over omega 1 plus omega 2 plus 1, then the expansions would agree. When you have like 4 and higher point propagators, then and you're wondering what happened, like acting particle 1 on particle 2, then there's always going to be extra finite terms that don't depend on 1 and 2, but like p3 dot p4, for example, and that extra finite term it makes it so that the soft expansions in 1 and 2 will commute from those higher point propagators, and they shouldn't give any more difficulties for this.
But what can't you have the say, I guess some of the other are like 3 and 4 also going soft? Like, do you have to worry about order limits for those as well?
Right. Yeah. So taking n particles soft, you probably need to worry about n plus 1 and fewer particle propagators.
Right. So would that give you would that give you new constraints, or are those all sort of implied by these constraints that you found that is required to ensure associativity involving the 3 particles?
Yeah. Well, yeah. It's plausible that it could give new constraints. It often happens that like you get to 3 point and then the rest is determined. But yeah, but that would be interesting to find out.
Thanks.
Yeah, this is super interesting. I'm not sure how it's all going to add up or what it all means, but let me just make a couple of comments. One is that when the Brown group put out their first paper, they had, just for pure gravity, they had 4 constraints. And then they realized that the first 2 were applied by the equivalence principle. And so now we know about more symmetries beyond the equivalence principle. So it doesn't seem impossible, and would be incredibly exciting if we had more constraints on low energy coupling coming from the more symmetries that we knew about. But in discussing that, one thing that you didn't mention is it's not obvious to me that couplings to massive particles can't affect these Jacobi identity calculations. We know that when we're doing energetically soft things, we can consistently stay in the soft sector, and but that's not true. Conformally soft massive particles look like they might be able to couple to calculations like this, but we don't understand exactly how to deal with them. But indeed, in the example of the heterotic string, if you just take the massive sector, it looks like something's going to be violated. There's going to be an all plus amplitude. But then when you include the stringy calculation with a massive field, so what it might be telling us is not that there's a constraint on coupling. What? Without the massive. I thought if you took the values of the couplings to scalars in the Brown papers, at least this is what they said in their original paper, that if you take the values of the coupling to scalars that are given a low energy effect of the interaction of the heterotic string, that you get some kind of violation of associativity. That's what they say. Maybe it's wrong.
That's what we initially thought, but there are two scalars, and there's the axion and dilaton, and the contributions add up such that the constraint is still satisfied.
Oh, is this about how you need a neutral scalar and one colored scalar?
No, this is in the gravity case.
Oh, okay.
So there's a mistake in the paper, you're saying?
Yeah, which we corrected.
You've corrected.
Yeah.
Good. Okay. Oh, that's interesting.
Yeah. The stuff, the things I've said in this talk were I had massless theories in mind, like the properties of propagators and dot products of momenta. I used some massless properties, but but I think some of the statements should apply to theories with massive particles too, like once you do a soft expansion, I think you will only get poles coming from the collinear part of the amplitude rather than the non-collinear part.
So is it now the case with the corrections in the paper that all known string compactification satisfy the constraints required by associativity?
I think at least the heterotic string example that we thought of initially does, and bosonic doesn't.
Yeah, besides bosonic, which is not consistent. But so, wait, so it's an open question whether all known string theories satisfy these constraints?
At least to me, I haven't thought about
Because
it.
in swamp world, this would be a reason to make a conjecture that these constraints are a law of nature, right?
Yeah, we haven't thought about all possible compactifications, but just the one that we brought up that definitely does satisfy the.
Well, it would be super interesting if there was some kind of conspiracy in string theory that that associativity, this kind of associativity violation did not occur for any of the known effective Lagrangians. That would be interesting. But there are lots of other things that come into mind, like making massive particles are important. Yeah, I'm not sure what the right way to think about it is. And by the way, on this, what Dan's doing, it's true that in some cases, 4-point things like this can have to do with curvature, but there are also funny cases even in ordinary conformal field theory. If you do a calculation of an ordinary conformal field theory, and you try to compute the curvature on the moduli space of marginal deformation, you're effectively wanting to work in Riemann normal coordinates. And if you're not very careful, you get 0. There's problems with coincidence of operators or whatever. So that also looks like something that you really have to go a little bit outside the usual formalism of ordinary conformal field theory to see these things. So I would imagine there would be examples in ordinary conformal field theory where calculations would give things that look like violations of Jacobi identity. Something that would calculate this curvature might look like it violates Jacobi identity because some naive calculations of it give 0.
Yeah, we gotta keep trying and be careful.
To do those calculations in conformal field theory, you have to actually break scale invariance, and then in some way, which gets you into all kinds of trouble, and then you have to take it away. Yeah. Those are hard calculations.
Which one was the laser? Did you use it or no?
Yes, second from the top is the laser, and then third from the top.
Okay. Yes, I did. Sure.